Lesson on electromagnetism and magnetism, and we are going to look at permanent magnets first and then on to how to create an electromagnet. Most of this is going to be revision, but if we bear with me, we will get through the material. Okay, first of all, with magnetism, we need to understand the following ideas: that you can get materials which are magnetic, naturally magnetic. That's how they discovered magnetism in the first place, when iron set in the Earth's core in a certain way and created a magnetic effect. But these are not just left to iron. There is also cobalt and nickel that are particularly magnetic, and of course any alloy of the above. Most popular is steel, and you need to appreciate that steel objects will be magnetic. Now, those magnetic materials will give rise to two types of magnets. One of them are known as hard, and the other one is known as soft. Now, hard magnetic materials are one that keep their magnetism. And soft magnetic materials are ones that can become magnetized. However, when the magnetic material is removed, they lose their magnetism. So they become magnetized, but are not permanent magnets. Okay, good. So I suppose the hard magnets are going to be regarded as permanent. And those are the ones that you're most familiar with in the labs. So what are the basic ideas of magnetism? Well, I'm sure you've all seen a simple bar magnet. And we have a top, a north, and the bottom, a south. Now, what does that actually mean? Well, these magnets and magnetic materials exhibit forces on them, and those forces often align themselves to the poles of the Earth. So therefore, it made sense to call one north and the other south, because it aligns itself to the North Pole, and this one aligns itself to the South Pole. However, that does mean something. We'll come on to the law of attraction in a minute. Good, so these are the poles. And from the poles, you have these magnetic field lines, which I'm sure you've seen with iron filings that spray out from the magnet, as so. And these can be detected by either iron filings or indeed plotting compasses. Two ways of doing it. The iron filings I'm sure you've seen. However, the plotting compasses are small little compasses which have a little arrow, and the arrow aligns itself to the magnetic field. Now I suppose we still haven't, let's draw another one in there actually. I suppose we still haven't defined what we mean by the magnetic field. Well, the magnetic field is what would happen if you placed what does magnetic field actually mean? Well, it's if you placed the North Pole in the vicinity of this magnet, then it shows you the direction of force experienced. In other words, if I was to place a magnet, a north end of a magnet here, what would happen? Well, it would feel a force in this direction. And as it got close to the south, it would feel a force in that direction until it felt a force directly attaching itself to the south. So I suppose that really brings light the law of magnets, and that being that if we have two magnets, which one end was the north and the other end was the south, then what would happen is this would feel a force of attraction, because opposites attract. Not to be confused with electrical current, this is magnetism and it's completely different. Well, at the moment it is, you'll see how it links together a bit later on. However, this is a different rule altogether you should bear in mind. And if you have north and a north, or a south or a south, then what you have is they will repel each other and push themselves away. And why is this? Well, actually, the magnetic field lines actually start to add to each other or subtract from each other. So if we're familiar that this is the magnetic field lines of ordinary magnets, not in the presence of the other, and it goes north to south, our magnetic field lines as shown above, then what happens is these field lines start to add to each other and produce this wonderful uniform magnetic field. And you'll notice that we'll use that quite a lot in the future topics to come, a uniform magnetic field. However, when you've got north and north competing, then you get this very sort of aggressive line of these field lines competing against each other, never crossing. And actually the point in there is actually no magnetic field at all. It's a technique we use to shield magnets from one another. Okay, so like charges repel, opposite charges attract. They can be identified by using iron filings or plotting compasses. Plotting compasses show where the magnetic field is, which is, in effect, if you placed a north pole in this vicinity, where the north pole would experience a force. Good. This does bring it to light one other effect, and that is that if the north magnet aligned itself to the magnetic field of the Earth, and north is pointing to the north, then actually what that means is that inside the Earth we actually have a south pole at the top, magnetic pole, and a north at the bottom in order for this to be attracted. What we often say, or we call them north poles, but that often means north seeking. It's a subtlety to bear in mind. Superb. So what do we need to talk about next? We've got, these are the static magnets, and we should probably next talk about what happens with electromagnets. Okay, now with electromagnets things are slightly trickier, much more difficult in actual fact, because whereas all that we talked about before was talking about 2 dimensions, which were easy to talk about, electromagnets talk about 3 dimensions. So we need to be happy about the concept of objects going in and out of a page. Let me just draw in 3 dimensions what I mean. If we have this piece of wire that travels through a sheet of paper, then what we need to be aware of is that currents create magnetic fields. Okay, so if there is a piece of wire with a current flowing through it, then it creates a magnetic field. How do we draw this a little bit better? Well, if it's going up, what we do is we imagine the piece of paper in 2 dimensions, and we imagine it, this piece of wire, coming out of the page. I hope you can see that. It's going up, and now it's coming out of the page. So what we do is we place a dot. So this is out of the page. And that represents, imagine the tip of an arrow. If it's coming towards you, all you see is the dot. However, If it were going into the page, we put a cross. Imagine the back of the arrow with the flight feathers. This is into page. Okay, so because we're working in 3 dimensions, you must become competent in understanding what that means. Okay, essentially, how do we work out what the magnetic field around a current carrying piece of wire is? Well, it's actually, you use your right hand. I'm going to draw a terrible, I'll show you there, your right hand grip rule it's called, whereby your thumb indicates the direction of the magnetic field, the current, and your fingers indicate the direction of the magnetic field. So if this were coming out of the page and I put my right hand up, just put right hand grip rule. Then the magnetic field will be turning around in a circle in this direction. Take a look at my fingers again. Thumb up, fingers around. However, if we're going into the page, my fingers are going the opposite direction. And therefore, if you imagine this is synonymous with that, drawn in a different way, what we have going on here is we have in this plane magnetic fields circulating. And further out. Okay, so easy to see in one instance. But we might have a situation where we might build it into something a little bit more complicated. So let me just show that in 3D. Apologies for the drawing, this is going to get a bit messy. A piece of wire comes up. We're going to bend that piece of wire over, and then it's going to go back out the same piece of paper. The current is the same throughout the same bit of wire. So we have the current coming up through this side and down through that side. If I was to draw it in its other format, I would draw it as this. It's coming out of the page, it's going into the page, So with my right hand grip rule, I'm going to have this type of magnetic field working in one direction and the opposite magnetic field, though the same shape, in the other direction. What we see is we see a building of the magnetic field through the middle with a supporting. So in effect, I have a building of the field in the middle. And it's not too hard to see how this can be continued in a coil of wire to provide the same type of magnetic field as that which we gained in a bar magnet. So this is where, hopefully, if we turn it slightly on its side, hopefully this works. So this piece goes back underneath, back out to the second one, it goes back underneath and out to the third one, back underneath to the fourth place, and back down. So hopefully you see a coil of wire. The current's coming in that way, out that way, so we have this direction, and back out again. Now if I was to draw that as a sort of 2-dimension, what we have is we have a series of points in which it's coming out of the paper and a series of points going into the paper. So therefore, very simply, I draw in my magnetic field on each of these, right hand grip rule, up, and now it's going down, so drawing might be a little bit better. And so therefore what happens is this starts to strengthen in the middle into a nice uniform field. And around the edges, of course, we have a spraying out. So this, a coil of wire, which is also known as a solenoid, has the same magnetic field as a bar magnet. With this side, of course, being south, and this side, of course, being north, because we know that magnetic field lines go from north to south, and this would spray around this side as well. Okay, so this is where it's tricky. Now we must bear in mind right-hand grip rule. It's 3 dimensions. We have one plane is working with the magnetic field, another plane is working with the electrical current. Do not, if you were given a picture like this of a coil of wire, what people often start doing is they often start drawing some strange thing where the magnetic field is going around the wire, or even going around the ends. It's none of that at all. Try and think nice and cleanly in different dimensions. Okay, we're going to make use of some uses of the electromagnets. And we're going to use 3 uses. One of them will be turning on a very bright light. And because this is a very high voltage, it might be a light, it might be a starter motor on a car, it might be, setting up kick-starting a power station if you need to. You turning that on could run a risk of you getting electrical shock. So what you do is you have a secondary circuit, which is much safer. And then when you move that switch, it turns on this relay, which then closes the larger circuit. So this is called a relay, whereby you're using an electromagnet to close another circuit. Okay, let's think about one last example. An electric bell. This is a little bit trickier to draw, but I think you've all seen this set up as a horseshoe magnet that's attracting a bar, and on the end of the bar is a hammer and the bell. Okay, we have a contact. Of course, we've made this electromagnet. And the electromagnet, one end is connected to the bar, and the other end, through a battery, is connected to this contact point. This has also got a springy bar, so it's spring-loaded, so it wants to go this way. Okay, now, when the battery is connected, we have a strong electromagnet. So point 1 is that the electromagnet is on. Okay, when it's on, the bar is attracted. So bar attracted. That in turn, 3, the hammer hits bell. However, for point 4, this bar is then pulled away from the contact. And that leaves us with a broken circuit, because you no longer have a complete circuit running all the way around, because you no longer have this connection. So it breaks circuit. And that switches off electromagnet. Of course, now the electromagnet is switched off, because this is a springy bar, it pings back towards the contact. And when it returns the contact, it then makes the connection again, the electromagnet comes on, and we go through a complete cycle all the way again. So therefore you get this repetitive motion, or the repeat hammering of the bell. Okay, I hope that all makes sense. It's just a lot of recap, and it's just the beginning stage before we kick off with some really exciting electromagnetism, like motors and generators. And also, there's very little problem solving in some ways in maths. It's going to be lots of understanding diagrams and where field lines act. Hope that makes sense.